to the notes on 4.8. This is over Gaussian elimination. So before we can talk about that, we need to talk about an augmented matrix. So an augmented matrix is just a way for us to write a system of equations as a matrix with our solutions in a single matrix, as opposed to a separate matrix where we're going to use inverses to solve. So each row in our matrix represents the equation of the system. So write an augmented matrix to represent the system. So given this system here, let's turn it into an augmented matrix. It's real easy. Write your matrix bar, and you got 3, -4, 12. And then we have 2, 9, 20. And then you just draw a bar like that to kind of separate your coefficients and variables and answers or solutions by themselves. You can do this with 3 by 3 as well. So this would become 1, 6, 1, 4. Our bar right there. Set up the rest of the matrix. And I got -1, 0 because there's no y term, 3, and -6. Then I have 2, -1, 0, and 14. That's how you'd make an augmented matrix from the system. And the nice thing is you can go backwards too. So if I go backwards right here, this becomes 3x plus y equals 5, and -2x plus 2y is equal to 7. Same thing over here. I have x minus 3y plus 2z is equal to 6. I also have y plus 4z is equal to -8. Lastly, I got 2x plus 3y plus 5z is equal to -4. So going between these two things, not all that crazy, pretty straightforward, and really not that interesting, but the reason why we do this is so we can turn the matrix into either row echelon form or reduced row echelon form. So first let's talk about row echelon form. So with row echelon form, all rows have zeros at the bottom of the matrix. So all rows consisting entirely of zeros occur at the bottom. All right, none of the examples here have that, but if you have a row of all zeros, put it at the bottom. So for each row that does not contain entirely zeros, the first non-zero entry is 1. This is your leading one. So like in these, my first non-zero entry is always 1. Okay, so you want it to be in kind of descending. It looks kind of like a pyramid. Okay. For 2 successive non-zero rows, the leading one in the higher row is further to the left than the leading one in the lower row. So notice that diagonal shape that we just talked about. Okay, so reduced row echelon form just takes row echelon form and goes a little bit further, and that means that every single column has a leading 1 and has zeros in every position above and below the leading 1. Okay, so you see how this has a leading 1, 0 below, leading 1, 0 above. And then right here, leading 1, 2 zeros below, leading 1, 0 above and below, leading 1, 2 zeros above. And then you have your values here. Same thing with numbers. Now the question is, why is this form helpful? I think the easiest way to show that is to take this one and turn it back into a system of equations. You get x equals 4, y equals 3, and z is equal to -2. Now this is really, really nice because those are the answers. That's literally why we're doing this. We're trying to get it to be the answers. So let's look at a couple of examples next. So Gaussian elimination method. So this is what we're actually talking about. So you can use row operations to solve a system of equations using an augmented matrix. So you can use the following row operations. We can interchange any two rows, multiply any rows by a non-zero constant, add one row to another, or add a multiple of a row to another. Remember, adding is the same as subtracting, just giving it a negative. So let's try this. So example 3 gives us this equation here. First step is always to turn it into an augmented matrix. So that's going to be 1, -3, -17, 2, 1, 1. Okay, so when I do these operations, I like to write down what I'm doing. So for instance, looking at this, I see, well, I already have a 1 right here. So what I want to do is get a 0 right here. Well, I can do that by taking 2 and subtracting 1 times 2. So what I'm going to do is I'm going to replace row 2 with row 2 minus 2 row 1. So I'm going to take row 2 and subtract or add -2 times row 1. So what that is going to give me is 1, -3, -17. So I just rewrite that same thing I had already used. And then I do 2 minus 2, which gives me 0. 1 plus 6, which gives me 7. And then 1 plus -2 times -17, which is +34, so this gives me 35. Okay, so a little bit of stuff went on there, so you may want to pause it and go back and kind of see what happened. I did row 2 minus 2 times row 1. So 1 times -1 minus -3 times -2. So 1 plus 6 gives me 7. Okay, from here I see, well, if I were to take row 2 and divide it by 7, or multiply by 1/7, I'd have a 1 right here. So let's do that. So I do R2 becomes 1/7 of R2. All right, and that just is, I get 1, -3, -17, 0, 1, and 5 right here. Okay, and my final step, maybe label these 1, 2, my final step 3 is going to be to take R1 and replace it with R1 plus 3 R2. Okay, that's going to get rid of this -3 right here and make it 0, because -3 plus 3 times 1 is 0. So that's going to become 1, 0, and then I got -17 plus 3 times 5. So -17 plus 15 gives me -2. And I got 0, 1, and 5. Okay, now this notation here, writing down your steps, really helps you understand what should I leave, what should I keep, and what should I change. So the answers here are x equals -2 and y equals 5. Okay, with a 3-variable system, same process, just a lot of stuff going on. So I'm going to combine some things in the effort to make this go a little bit quicker. Make sure you pause and go back and kind of see what's going on before you do this. Okay, so first step is to turn it into an augmented matrix. This is 1, 1, -1, -1, -1, -3, -3, -9, 1, 2, -3, -8. Here's my augment line like this. Okay, so first step, I'm going to notice that in my first column, I got a 1, a -1, and a 1. I want to keep this 1 right here, so I'm going to leave row 1 the same. So let's write that down again. 1, 1, -1, -1. Okay, but to get rid of the 1 in row 2, I'm going to replace row 2 with row 2 plus row 1. And then at the same time, I'm going to replace row 3 with row 3 minus row 1. Okay, so you can do these operations and leave them the same. All right, so R2 plus R1 gives me 0, -2, -4, -10. And then R3 minus R1 gives me 0, 1, -2, -7. All right, next step. Well, I noticed there's already a 1 right here, and in my operations it said I can interchange any two rows. Right up here if you didn't believe me. Yep, right there. Okay, so I'm going to do that. I'm going to switch R2 and R3. Let's write that down. Switch R2 and R3. Okay, so let's write down that new matrix. I got 1, 1, negative 1, negative 1, 0, 1, negative 2, negative 7, and then 0, negative 2, negative 4, negative 10. Okay, next one. Well, I noticed that there is now a 1 in this entry right here. So let's keep R2 the same. So I got 0, 1, negative 2, negative 7. And then in order to get rid of everything there, I'm going to do R1 becomes, so R1 becomes R1 minus R2. And then I'm going to let R3 become R3 plus 2R2. Okay, so R1 minus R2 gives me, whoa, that was a mistake. Turns out can't bump this with my hand, guys. Very exciting. 1, 0, 1, 6. And then I got 0, 0, negative 8, negative 24. All right, this is getting exciting. We're getting closer to our reduced row echelon form, which is really what we're looking for. And to do this next step, we're going to let R3 become negative 1/8 of R3, because that'll get my negative 8 here to a 1. That's what I want to look for every single time. So this is going to become 1, 0, 1, 6. And I did not leave enough space with this bracket. Make it a little bit bigger, make this one better. That's not a bracket, but whatever. Okay, so I got 0, 1, negative 2, negative 7, and this becomes 0, 0, 1, 3. Okay, almost there. Last step. I notice that everything is good, but the one that's best is R3. So let's leave that the same this time. So I got 0, 0, 1, 3. Then what I'm going to do is I'm going to let R2 become R2 plus 2R3. I'm going to let R1 become R1 minus R3. Okay, and this gives me the augmented matrix 1, 0, 0, negative 3, 0, 1, 0, negative 1. And this tells me my solutions are x equals negative 3, y equals negative 1, and z is equal to 3. And there you guys see, this is a way more entertaining way of solving a system of 3 equations, 3 variables, than using elimination, because you can clearly see what step, you can see what's going on, and it's just kind of nice. All right, thank you very much.